When we're trying to find absolute extrema, what we're looking for is the absolute highest and lowest point on a graph. So let's say I had a graph that looked like this, like that, okay? And I want to find the highest or lowest point on the graph, but on an interval, on a snapshot, like a window on your graphing calculator. All right, so let's say I want to take this snapshot right here, boom. Okay, in that window, I want to find the highest and lowest point on the graph. So if you could hopefully look at it, can't you tell this is the lowest point, and can you tell that's the highest point? All right, that's what absolute extrema is you're trying to find the highest or lowest point on the graph. Now you could change your window, like I could do the window over here. You could do the window anywhere on a graph, and you're trying to find the highest or lowest point. So how do you do that though without graphing? And that's what we're going to get into. With a graph, it's real simple. Oh, look at it, there it is, yay! Real quick and easy, yes. But a lot of times in calculus, it's how to do things without a graphing calculator. So here's a little procedure we use to find absolute extremas without a calculator. First thing we do is find critical numbers. Now a critical number is where the first derivative equals 0 or does not exist, and the value has to exist. So there actually has to be a coordinate there. It can't just be a hole or an asymptote or something. So the coordinate has to exist, and at that coordinate, the derivative is 0 or the derivative does not exist. Now, critical numbers tend to be hills and valleys, tend to be relative extremas. Anywho, like there's a hill, valley, it's kind of a plateau. Anyways, so first thing we find critical numbers, then we find the coordinates of the critical numbers, then we find the coordinates of the endpoints, and then we see which of those is the highest and lowest. That's the procedure. And we'll talk about after we're done, why does it work? Why does that work? Why does that help? Let's see. So here we go. First thing we do is find the critical numbers. Okay, so we take the derivative equal to 0, or it does not exist. So let's take the derivative of this function. So what is the derivative? Well, f prime x is equal to derivative of x to the third is 3x squared. Derivative of 3x squared is negative 6x. And the derivative of negative 1 is 0. Alright, now we set it equal to 0. Right, derivative equal to 0. We find a c value, a value that works for it. Let's see. So I want to set this equal to 0. So I put 0 equals this derivative, but I'm going to factor this because in solving it, you're going to need a factor to solve it. So do you see a GCF of 3x, the greatest common factor of 3x? What's left when you pull a 3x out of both of these? You're left with x, because 3x times x is 3x squared. 3x times what is negative 6x? Negative 2. Alright, so we set our derivative equal to 0, like we said there. Alright, and we solve it to see what that is. Okay, so what would be the values where my first derivative equals 0? So what we do is, it's called zero product property. We set each of these equal to 0. So we set 3x equal to 0, and we set x minus 2 equal to 0. Alright, once we get there, we're trying to solve these. What would make this 0? Well, if you divide by 3, you got x equals 0. And here you add 2. So, I just solved this function. The answers are 0 and 2. What that is saying is, at 0 and 2, this graph has a slope of 0. Okay, at 0 and 2, this graph has a slope of 0. And these numbers are called critical numbers. They're pretty critical. Maybe that's why they're called critical numbers. Alright, now, from there, what we do is find the coordinates of the critical numbers and find the coordinates of the endpoints. So what that means is I basically want to plug in these two values and the endpoints of the interval. So we have an interval here. So are these two values both in the interval? Yes. Now, if these weren't in the interval, you don't need to worry about them. Technically, the critical numbers have to be in the interval. Are these? Yes, they're in the interval. So we want to plug in this, 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 and this. So here we go. Let's first do the critical numbers. So let's do f of 0. Okay, and we're going to do f of 2. So we're going to find each critical number, all right, into the original function and see what the output is. That'll be the coordinate. So we have 0 cubed minus 3 times 0 squared minus 1. All right, what is that going to be? Well, I love zeros. 0 cubed, 0. 0 squared, 0 times 0. Oh, equals 0, and that equals -1. So that would be a coordinate of 0, -1. All right, let's plug 2 in. 2 cubed minus 3 times 2 squared minus 1. What would that equal? 2 cubed, 8. 2 squared, 4. What's 8 minus 4 times 12? 8 minus 12 minus 1. What would that be? What would that be? Is that -5? So we have 2, -5. Okay. So did we find the coordinate for the critical numbers? Yes, we did. Okay. Now the coordinate for the endpoints. Okay. Endpoints are -2 and 3, because that's the interval we're doing this in. So we got -2. We're going to plug in, right? And we're going to plug in, the other point is 3. Okay, so we plug -2 in. So -2 cubed minus 3 times -2 squared minus 1. What would that be? What are we going to get there? Well, this becomes -8. This still is -12. So we have -8 minus 12 minus 1. Ooh, what is that? What is it? -21. All right, and this would be -2, -21. All right, and next we're going to do 3. So 3 cubed, kind of long, sorry. I'm getting sick of all this. Plug in 3. 3 cubed, what is that going to give you? 27. 3 squared is 9. 9 times -3 is -27, and then minus 1. That gives us, that's 0, minus 1 is -1. So at 3 we got -1. All right. Whew. All that work. Did we find the critical number coordinates and the endpoint coordinates? Yes, we did. Which is the highest? Which is the lowest? Basically, all you do now is look at these outputs. Okay, so the highest or the biggest value is your absolute max. The lowest is the smallest value, or your absolute min. So what's the smallest value? Hopefully you can see it's -21. So this right here is our absolute minimum. Bam, we are done with that. And then we find the absolute min, max. That's the smallest. What's the largest of these? Well, the -1, but there's 2 of them. So they both are your absolute max, because they both are the highest point. All right, so this would be an absolute max, and so would this. So there's 2 absolute maxes, and this is your absolute min. Now, so you just follow this procedure. You can always find your absolute maxes and mins. Okay. Now, there's a couple things of why does this procedure work? What did I do? Why did I do it? Here we go. All right. First of all, critical numbers are where the slope is 0 or does not exist. Remember, I didn't have any does not exist here, but watch out for it. Now, when you have a slope of 0, think of this. Critical numbers if you have a graph that goes like that, do you understand? A slope of 0 is a hill or valley, which could be the highest or lowest point on a graph. Can you picture that? A slope of 0 is called a tangent line of 0, which horizontal tangent lines, which those are hills and valleys. Those are very critical points. So at these 2 points, you're going to have either a hill or a valley, one of those two. All right, which those could be the highest or lowest point on the interval, as well as the edges could be the highest or lowest point on the interval. So that's where we do critical numbers and endpoints, because the edges of it could be critical numbers, as well as the endpoints could be critical numbers. All right, sorry, not critical, could be absolute maxes and mins. So critical numbers are important, they're critical. And one more thing you have to worry about is sometimes for absolute extremas we have open intervals. Like what if that was an open interval? We don't include 3. Well, if we don't include 3, this would not be an absolute max. So we would not include this one because it would be open. So that would be your absolute max, that would be absolute min. Okay, if -2 was not included, it wouldn't matter because it's neither absolute max or min, but you still find it. Okay, so -2, sorry, right here. Actually, I said that wrong. -2, I pointed the wrong one. At -2, what is it? It's absolute min. So if this was an open interval, guess what? -2, there would be no absolute min at all. So if this was an open interval, and this was a closed, say closed, basically if -2 is not part of the interval, you would have no absolute min. A lot of people, what they do is they go, oh, I don't include that, so that's not it. So that's not an absolute min. That's the smallest value. No, because that would have been the absolute lowest point, but it doesn't. It's not part of it. It's an open circle there. Remember, if you had an open bracket, it would be an open circle there. It would still be where the absolute min should have been. You can't just go and say that's the lowest, because if you think about the graph, there'd be a value just like a teeny bit above that, which would make the min kind of hard to see. It'd be like a decimal right next to -21. Okay, that might be confusing you. But be aware, sometimes these will be open brackets, which you still want to include them in your checks. And then once you check it, if it is open, you just cross it out and say it doesn't have that. So again, if that was an open interval, there would be no absolute min altogether. That would not become the absolute min. Okay, so watch out for that. All right, a lot to take in. Absolute extremers are very important. Follow this procedure. Look for the highest and lowest points depending on if they want absolute maxes or absolute mins. It's a very important concept, and good luck with them.